All right, so intro to confidence intervals. A plausible range of values for the population parameter is called a confidence interval. So using only the sample statistic to estimate a parameter is like fishing in a murky lake with a spear, and using a confidence interval is like fishing with a net. So we can throw the spear where we saw a fish, but we'll probably miss. If we toss a net in that area, we have a good chance of catching a fish. So if we report a point estimate, right, say we sample 100 people and ask them who they're voting for president, and we report the percentage of people who say that they're voting for Tony Stark, probably that's not going to be exactly the percentage of all Americans who are voting for Tony Stark. So we report the point estimate, we probably won't hit the exact population parameter. We might be close, but we don't have any way of saying how close. If we report a confidence interval, a range of plausible values, we have a good chance that our population parameter, in this case the proportion of people voting for Tony Stark for president, will be in that range. So, a random sample of 50 college students were asked how many exclusive relationships they've been in so far. The approximate 95% confidence interval is given as 2.7 to 3.7. Which of the following is the correct interpretation of this confidence interval? We are 95% confident that A, the average number of exclusive relationships college students in this sample have been in is between 2.7 and 3.7. No. We know what the average number of exclusive relationships college students in the sample have been in. We don't need a confidence interval for the sample. We know the exact average for the sample because we polled everybody in the sample. So you don't ever have a confidence interval about the sample. The confidence interval is about the population. Okay? We are 95% confident that college students on average, right, college students in general, on average, have been in between 2.7 and 3.7 exclusive relationships. The 95% confident, it's not about a randomly chosen college student, right? This is the average. So not about a randomly chosen student. And it doesn't tell us that 95% of college students have been in 2.7 to 3.7 relationships. It's a confidence level about the average. It doesn't tell us about a proportion of the population. Right? So we're trying to capture the true average or the true proportion if we're doing a confidence interval for a proportion. We're not trying to capture 95% of students. So, on your AP test, you will almost undoubtedly be asked to interpret your confidence interval. Here's how you do it. We are blank % confident that the parameter is between blank units. All right, so we are 95% confident that the average number of relationships for college students that college students have been in is between 2.7 and 3.7 exclusive relationships. Confidence level, parameter would be the number of relationships, interval, units. Memorize this. It's important. Every time you're interpreting a confidence interval. If we want to be more certain that we capture the population parameter, that is, increase our confidence interval, should we use a wider interval or a smaller interval? If instead of being 95% certain, we want to be 99% certain, let's say, Should we use a wider interval or a smaller interval? Think about it. A wider interval. So can you see any drawbacks to using a wider interval? So, little Garfield comic. Weatherman says, taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. Right? That guy is pretty confident. I can also be pretty confident that the high temperature will be between 40 below zero and 200 above. That's, I can say that with near 100% confidence. Not technically 100% confidence, but pretty darn close, right? So I can be very, very confident, but this interval is not useful in any way. That does not tell me what, clothes I should pick out to wear tomorrow if I'm going shopping. Conversely, I could also be 5% confident that the temperature is going to be the high temperature is going to be between 41 and 42.2, right? Very narrow range, but I'm only 5% confident. I'm very likely going to be wrong. That's also not useful. So it's not useful to have a narrow range if I have low confidence, and it's not useful to be very confident in a very wide range. So one of the things that we consider is striking a balance between the two, right? A confidence level that's high enough to be useful, but also an interval that's narrow enough to be useful. And for this reason, we usually settle on a 95% confidence level. That's just one of the common confidence levels. A lot of our example problems are going to use a 95% confidence level. And the reason that we do that is that that's a pretty high confidence, 95%, pretty good. But also generally produces a narrow enough confidence interval that it is useful for what we're doing. The width of the interval doesn't just depend on the confidence level. It also depends on what's called the standard error, we'll talk about in a minute, which is partially based on the number of things in your sample. But if you hold that standard error constant, you can change the confidence interval by changing the confidence level. Okay? So, under certain conditions, we can assume that the sampling distribution is approximately normal. Remember what those conditions were? Samples are independent, NP and N1 minus P are at least 10, less than 10%, our sample is less than 10% of the population. This is for a proportion. If it's a mean, then we would use the central limit theorem, and is at least 30 as our large counts instead. In a normal distribution, predictable percentages of data fall within certain standard deviations of the mean. These are called z-scores, right? The z-scores, we can use the z-score to tell us what percentage of the data falls within a certain number of standard deviations away from the mean. Our point estimate is our best estimate of the mean of our sampling distribution, right? So if I sample 100 people and 53 of them tell me they're voting for Tony Stark as president, 53% is my point estimate. That's my best estimate for the true percentage of the entire population that's voting for Tony Stark for president. And the true population parameter is also the mean of the sampling distribution. The standard error is our best estimate of the standard deviation of the sampling distribution. Talk about standard error in a second. So, we construct our confidence interval to be the point estimate plus or minus a certain number of standard errors, depending on our confidence. So we construct a sampling distribution that is approximately normal because it meets our conditions, and we put our point estimate, either p hat or x bar, as the mean of that population, sampling distribution. We don't know the mean of the sampling distribution, but that's our best guess. And then we go a certain number of standard errors. For a 95% confidence, it's about 2. Because 2 standard deviations encompasses about 95% of a normal distribution. And that gives us our confidence interval. So if the point estimate is in fact the mean of the sampling distribution, then our standard error is our standard deviation, then say 95% of our point estimates, if we took a bunch of different samples, would fall within 2 standard errors of the mean. How many standard deviations away from the mean encompass 95% of the data? I just told you that. But you can do it on your calculator, right? So inverse norm, remember that you're doing 95% in the middle. So if I want 95% in the middle here, that means 2.5% on each tail. So if you're doing inverse norm, if you want this z-score, you're going to need to put 0.025 instead of 0.5. When you're finding z-scores, always use 0 and 1 for your mean and standard deviation. So if you do that, that's going to give you, it's 1.96. If you get the little wizard that gives you the left, center, right for the tail, then you can do 95 and do center, right? You want the center 95, and that'll give you the z-score. That only works if you have the option to click center. If you don't have the option to click center, you have to divide the leftover percentage by 2 and do it this way. So for 95%, if you do this, it's 1.96 approximately standard deviations away from the mean. For 90, so if you do inverse norm of 0.05, I think is 1.64. Pretty sure. Double check it. Do it on your calculator. And 99 would be inverse norm of 0.00501, which is going to be 2 point something, 2.3-ish, I think. I don't have a calculator on me right now, but try it. Should be somewhere in there. Right? So, the anatomy of a confidence interval. Your confidence interval is your point estimate plus or minus the margin of error. If you see, like, poll results on the news around an election, at the bottom, so what they usually do is they report the point estimate, and then at the bottom, they will report a margin of error. Usually the margin of error is about 3%. Just based on the standard size of the polls that they do around elections. I usually see margins of error of about 3%, or 3 percentage points. So, you have your point estimate plus or minus your margin of error. The margin of error changes as the confidence level changes. The Z this is your z-score. This is based on your confidence level. So this is based on the confidence level, and you get it by doing the inverse norm for whatever confidence level you have. Commonly used confidence levels, 90, 95, 98, 99. 95 is definitely by far the most common, which is why I know off the top of my head what z-score it goes with, because it's used all the time, 1.96. But sometimes you see 90 and 98 and 99. There are different reasons for having different confidence levels. If you're doing something, involving a medication or some kind of drug trial, you would want a higher confidence level because it's important to be really confident. If, your numbers aren't that good, sometimes you go with a 90% confidence in order to narrow your confidence interval down into something like reasonable. I'm making fun of statisticians a little bit, but yeah, there are different reasons. It's about that trade-off between precision and accuracy, right? Between how narrow your confidence interval is versus how confident you are. So, using standard normal distribution, you can find a z-score for any confidence level. If you wanted to be 97.3% confident, why on earth would you want to do that? I don't know, but you could find a z-score for it. Just put it into the inverse norm. All right, so appropriate z-score for calculating a 98% confidence interval. Critical value is another word for this z-score. For a 98% confidence interval, it would be 2.33. Right? So on your calculator, inverse norm of 0.0101, going to give you a z-score here. You want 98% in the middle, which means 1% in each tail. And so that's going to give you 2.33. When you do the inverse norm, it's always going to give you, if you do it like this, it's going to give you a negative because it's looking at this lower tail. Because your margin of error, your confidence interval is plus or minus a margin of error, just get rid of that negative. Just drop the negative and report the number. Because that, the negative gets incorporated into this plus or minus. So you just drop it and report the number. It'll come back there. All right. Yay! Intro to confidence intervals.